As scientists and astronomers peer more closely and with ever more fidelity at nearby stars, they are discovering exoplanets, worlds outside our own solar system. Stars with planets were once thought to be a rarity. They are turning out to be the norm and not the exception. With some confidence, scientists now calculate there could be as many as 40 billion Earth-like planets in our Milky Way galaxy alone. The first exoplanets were detected in 1992, orbiting a pulsar, the remnants of a massive exploded star that was now a fast-spinning neutron star. With data collected from the Arecibo antennae in Puerto Rico, Alexander Volshan discovered 3 terrestrial planets orbiting the pulsar PSRB 1257 plus 12. Other pulsars have been detected with dust clouds and disks orbiting them. This suggests that these 3 planets are second generation. The original planets were destroyed by the stellar explosion, and a subsequent debris disk enabled these new planets to form. It was another 3 years before the first planet orbiting a G-class star similar to our Sun was identified, a gas giant like Jupiter orbiting 51 Pegasi every 4 days. 5 years later, another main sequence star was found to have multiple planets. Exoplanets were not easy to detect. They are tiny, their light smothered by the light of their star, and they are so far away. There are 3 main methods for planetary detection. The hardest is direct visual observation by a telescope, both on the ground and in orbit. Some 59 planets have been discovered this way. More indirect methods are employed, one of which is the radial velocity method. As a planet orbits, its gravitational pull causes the parent star to move back and forth. This tiny radial motion shifts the observed spectrum of the star by a correspondingly small amount because of the Doppler shift. With supersensitive spectrographs, the shifts can be measured and used to infer details of a planet's mass and orbit. The 3.6-meter telescope at La Silla, Chile, has such a spectrographic instrument called HART and is the leading exoplanet hunter. This is Tau Boötis, one of the first planets discovered utilizing this method. 51 light-years from Earth, this planet is massive, some 4 times the mass of Jupiter. So far, over 600 planets have been detected by this method. Another observational tool, and the most successful to date, is the transit method. A planet that passes in front of its parent star relative to us produces a slight dimming of the star's light, which can be detected by sensitive instruments. Some 1,200 have been located this way. Until now, it was expected that exoplanets would orbit in more or less the same plane and in the same direction as the star's rotation. However, new results unexpectedly show that many exoplanets actually orbit at a large angle to their star's spin axis. In the case shown here, WASP 8b, the orbit is completely reversed. There are other tools and techniques in the planet hunting toolbox, including microlensing, occultation and TTV or transit timing variation. Often more than one technique is used to verify findings. In fact, revisiting a planet after some time for verification can lead to surprising results, as in HD 189733b, a hot Jupiter-type planet. On revisiting it, Hubble discovered the atmosphere was being stripped from it by a violent stellar flare. With the Hubble Space Telescope dividing its valuable time between many varied tasks and objectives, a dedicated planet hunter called Corot was launched. The mission was led by the French space agency, CNES, with contributions from ESA, Austria, Belgium, Germany, Spain and Brazil. Launched in 2006, the mission lasted 7 years. It located 2 planets around the star Corot 7, one of which was the first found to display a density similar to Earth's. In all, it located 32 planets, and 100 others are awaiting confirmation. The NASA Spitzer Infrared Space Telescope was launched to study protoplanetary and debris disks around stars and the curious brown dwarfs, often referred to as failed stars. Spitzer's infrared capability quickly led to numerous planetary discoveries and infrared mapping of other known planets like hot Jupiter HD 149026b. Some 256 light-years away in the constellation Hercules, a planet dubbed a hot Jupiter, it is a sweltering 2040 degrees Celsius, the hottest planet yet detected, and also the darkest, reflecting no sunlight back into space. It speeds around its star every 2.9 days. A world just 2/3 the size of Earth, one of the smallest on record, and only 33 light-years away around the star GJ436, planet UCF-1.01 might be the nearest world to our solar system that is smaller than Earth. The planet, a rocky world, orbits so close to the star that the surface is probably molten. As with HD 189733b in the constellation Vulpecula, it appears to be tidally locked to its star, showing only one face as it orbits. Spitzer was able to distinguish the various temperatures of its clouds from 650 to 1700 degrees Celsius. Thermal imaging of these hot giants has provided more details of these distant worlds. In 2009, the game changed with the launch of the Kepler Space Observatory. As part of NASA's Discovery program, the Kepler Space Telescope was launched to survey and monitor a fixed field of stars of the nearby Milky Way trailing behind Earth. It observed around 165,000 stars, watching for any changes in their brightness. It has located over 1,100 planetary candidates.
Now these are candidates, but most of them I'm convinced will be confirmed in the coming months and years. That's more than all the people have found so far in history.
A veritable menagerie of planet types is emerging, like Kepler 16b, orbiting 2 stars, ice worlds and water worlds like Gliese 1214b.
The Kepler team announced today 1,094 new planet candidates, bringing the total roster up to 2,326. Of those, 207 are Earth-size, and we now have 48 that are in the habitable zone, 10 of which are smaller than 2 Earth radii. So these are planets that could potentially be rocky. So it's an exciting milestone because we are really honing in on truly Earth-sized habitable planets.
The combined surface and space-based system observations have led scientists to believe that planets around stars are the rule rather than the exception, and the average number of planets per star is greater than 1. Kepler has discovered at least 86 stars with multiple planetary systems. Kepler 11, for example, has 6 confirmed planets orbiting a Sun-like star.
The Kepler 11 planetary system is amazing. It's amazingly compact, it's amazingly flat. There's an amazingly large number of big planets orbiting close to their star. We didn't know such systems could even exist. There's certainly far fewer than 1% of stars have systems like Kepler 11. But whether it's 1 in 1,000, 1 in 10,000, or 1 in a million, that we don't know, because we only know one of them.
The growing number of confirmed planets is opening up new insights into planet formation.
We're learning so much more about the orbits of planets, the masses of planets, the sizes of planets, and we're just beginning. Kepler is still returning data, and we're going to learn a fantastic amount about the diversity of planets out there around stars within our galaxy.
Around each star is a circumstellar region called the habitable zone. Sometimes referred to as the Goldilocks zone, this is a region neither too cold nor too hot, where a planet could, under the right conditions, support liquid water at its surface, and in turn could support life. The first Earth-sized planet in a habitable zone was discovered around a red dwarf. Named Kepler 186f, it is just 10% larger than Earth.
Kepler 186f is the first validated Earth-sized planet in the habitable zone of its star. It's the outermost of 5 planets to orbit a star that is smaller and cooler than the Sun. This planet orbits its star every 130 days, and so this places it in the habitable zone, where it's in a region where it could have liquid water on its surface.
The star Kepler 186 is 500 light-years from Earth in the constellation Cygnus.
This planet, Kepler 186f, orbits a star that's cooler and dimmer than the Sun. So while we may have found a planet that's the same size as Earth and receives a similar amount of energy to what Earth receives, it orbits a very different star. So perhaps instead of an Earth twin, we've discovered an Earth cousin.
Believed to be a rocky world, its mass and density are yet to be determined.
This is one of the big milestones that we've been looking for in our attempts to find out if there are places just like home and if there's life out there. One of the big steps is to say, is there somewhere that looks, to all intents and purposes, like Earth? Well, we don't know just yet, but we know that there are places that at least look similar.
To date, over 48 Earth-like planets have been located within habitable zones. Gliese 581 has 4 known planets. The outer D planet is thought to be an icy planet that has migrated closer to the star and would thus be covered by a large and deep ocean. Kepler 62f is likely to have a rocky composition and is only 40% larger than Earth, making it the exoplanet closest to the size of our planet known in the habitable zone of another star. Kepler 62e orbits on the inner edge of the habitable zone and is roughly 60% larger than Earth. Other recent discoveries include Kepler 438b, 442b, and 440b, a super-Earth. The super-Earth exoplanet GJ1214b orbits its faint red parent star. This is the first super-Earth exoplanet to have had its atmosphere analyzed. It has a mass about 6 times that of the Earth and appears to be surrounded by an atmosphere of steam or thick clouds or haze. Based on observations, scientists believe that of the Sun-like stars, some 22% have an Earth-sized planet orbiting in the habitable zone. Assuming 200 billion stars in the Milky Way, that would be 11 billion potentially habitable Earths, rising to 40 billion worlds if brown dwarfs are included. Are any of these worlds close to Earth? In fact, yes. The closest star to our own is the well-known Alpha Centauri group, with the bright stars Alpha and Beta Centauri, plus the faint red star Proxima Centauri, the closest star to Earth. Alpha Centauri b is known to be orbited by an Earth-mass planet, making it the closest exoplanet to our solar system, a mere 4.37 light-years away, almost within our reach. Now in its fourth observing campaign, the Kepler spacecraft continues targeting 16,000 stars for exoplanets. It's estimated that the onboard fuel supply should last until at least December 2017. So far, Kepler has found an astounding 1,013 confirmed exoplanets around 440 star systems. The terrestrial telescopes continue to do the heavy lifting when it comes to verifying possible planet candidates. The HARPS spectrographic instrument at Vasilla, Chile, is being joined by the Next Generation Transit Survey, or NGTS. It will search for transiting exoplanets with a focus on discovering Neptune-sized and smaller planets. NGTS is designed to operate in a robotic mode. It will continuously monitor the brightness of hundreds of thousands of comparatively bright stars in the southern skies. ESO's Very Large Telescope at Cerro Paranal in Chile, composed of 4 individual telescopes, will be improved with the new next generation of adaptive optic system called SPHERE. Other improved technologies include the Gemini Planet Imager at nearby Cerro Pachon, now in operation, and the Subaru Coronographic Extreme technology currently being installed and tested. New, bigger and more powerful telescopes are in the pipeline as well. The 30-meter telescope planned for Mauna Kea, Hawaii, will have 492 small hexagon mirrors arranged together to form the primary mirror 30 meters across. The GMT, or Giant Magellan Telescope, will be built at the Las Campañas Observatory in Chile. It will consist of 7 8.4-meter mirrors arranged together to make up the primary mirror. Work on the mirrors is well underway. Extremely Large Telescope in the Atacama Desert is due for completion in 2024. It will have a 39-meter diameter mirror made up of 798 hexagonal mirrors and will be the largest ever built. It will enable scientists to study the atmosphere of exoplanets more closely. Space-based telescopes are advancing as well. The next generation infrared telescope, James Webb, is nearing completion as it goes through rigorous testing. A scheduled launch in October 2018 will put the 6.5-meter telescope in orbit as a replacement for the Hubble and Spitzer telescopes. Likened to the California gold rush, there are planets out there to be found, and the race is on. TESS, the Transiting Exoplanet Survey satellite, is scheduled to launch in 2017. TESS will scan the entire sky, searching for exoplanets using 4 state-of-the-art cameras. It will be able to determine the chemical compositions of exoplanet atmospheres. Also planned for a 2017 launch is Cheops. Its function is to characterize transiting exoplanets orbiting bright host stars. The satellite is a small package, roughly 1.5 meters square, with a life expectancy of 5 years. The European Space Agency has commenced a new program called Cosmic Vision, set to run from 2015 to 2025, with Plato, an exoplanet hunter, expected to be launched in 2024. Other projects underway include Pégase, under development in France, Exceed, the Exoplanetary Circumstellar Environments and Disk Explorer at NASA, and Finesse, the Fast Infrared Exoplanet Spectroscopy Survey Explorer, due to launch 2019. The Wide Field Infrared Survey Telescope, WFIRST, is another NASA observatory designed to perform wide-field imaging for the planet-hunting community. It will be fitted with a coronagraph instrument for direct imaging of exoplanets and debris disks. Another NASA New Worlds mission is the Star Shade project, scheduled for a 2019 launch. It will physically block the star's light with a parasol to allow direct observation of exoplanets. NASA is already thinking about a future James Webb replacement. Called the Advanced Technology Large Aperture Space Telescope, or ATLAST, it will be 2,000 times more light-sensitive than Hubble. If all goes according to plan, ATLAST could be launched between 2025 and 2035. With these new tools and technologies, it is only a matter of time before we are able to detect Earth-like worlds capable of supporting life. Perhaps one day, even a planet emitting radio or other signals indicative of a sufficiently advanced intelligent civilization. Finally answering that great question, are we alone? Our seafaring nature has translated well to the space age, sailing out into the unknown in search of riches of one kind or another. While Europe and Asia continue their interest in the resource-rich moon, the United States and NASA have set their sights on nothing less than manned missions to Mars. Can they manage to go shore to shore on the most dangerous of unknown seas, deep space? With low Earth orbit harnessed, it's time to look further afield. To build a spacecraft and rocket system to reach Mars is a mammoth undertaking, but if successful, it will return the United States to the top of the space achievement ladder. The first requirement? A space capsule able to carry 6 astronauts for a long period of time and return them safely to Earth. Orion is its name, and it has flown once already in a shakedown. The next flight will be an unmanned test mission past the Moon, followed by a third manned mission. The components for the vehicle are developed around the country, tested and checked, then passed on for assembly. The minutest bolt and circuit is designed, tested, redesigned and tested again. Slowly the systems come together with the aid of some breakthrough technology, particularly in manufacturing methods, new materials and processes. The first thing to notice is that NASA have gone back to the classic conic shape like Apollo, the safest design yet devised. Avionics, control systems, computer software and a glass cockpit, all state-of-the-art.
And the concept was to go with a glass cockpit, and what that means is that the instruments are all images on a computer screen. They are all on the glass. So rather than flipping a physical switch, the crew brings up a computer screen and flips a virtual switch, a little icon of a switch or icon of a valve. And with the exception of 7 panels right around the computer screens, which have about 60 switches, that is all of the cockpit of Orion happens on the glass. One big benefit is a weight savings because you don't have to have a physical switch. And having a physical switch, not only is there the weight of the switch, but you also have the weight of the wire to the switch. And you have to have the weight of circuitry that takes that wire and feeds it into the vehicle computers.
Because of Orion's size, its all-important heat shield is the largest one ever made, and new processes were required to manufacture it.
The Orion heat shield has got to be able to withstand landing loads on the order of 300 to 400,000 pounds. Because we're returning potentially from the Moon or beyond, and the flight duration from the time in which you commit to a return to the time you actually land, the weather conditions on Earth can be substantially different or difficult to predict. And so the Orion spacecraft has to be able to land in the ocean in a wide range of sea conditions, wave height, wave slope angle, and horizontal winds. That is what's driven us to a skin stringer architecture that utilizes a thick laminate composite skin bolted to a titanium substructure.
We bond on an ablator called the avcoat. The ablator is the thermal protection part of the heat shield. The very outside of the ablator actually gets hot enough that it decomposes, and that's the ablation part of it as opposed to an insulator like a shuttle tile.
Then come the ancillary structures and equipment that will ride with the capsule. The escape tower, designed and tested, will pull the capsule away from the main rocket in the case of an emergency. Adapter separation from the rocket's upper stage. Parachute deployment. The connecting adapter to the EMS. The EMS is the service module attached to the Orion in flight, supplying oxygen, water, power and heating. Built by ESA, it is based on their very successful ATV program, which delivered supplies to the ISS. It will also provide the main engine thrust for deep space maneuvering.
We have, in particular, very tight schedule in front of us. So everybody's working under a high pressure to meet the dates, and this requires a very close collaboration.
I see a very motivated team, and so far as an agency we are quite happy with the performance of the European industry.
The US Navy is tasked with retrieving the capsule from the ocean. At first they train in the pool, then calm waters, then the Pacific, and finally the real thing. Experts continue to evolve the process and training in readiness for the day when a manned flight returns from deep space. This is the RS-25, the Ferrari of liquid rocket engines and the main engine from the Space Shuttle program. Economically repurposed for the Space Launch System, 4 of these engines will power the main stage of the rocket. The main solid rocket boosters of the shuttle program also have a renewed life in the SLS. With another 2 segments added, the boosters will thrust for over 2 minutes.
This project has been a real fun effort in trying to take a heritage booster that had many, many years of reliability and great performance and evolve it into something bigger and better.
When we first undertook this design and qualification for the new booster, part of the mission was to make the booster more affordable and more modern, and of course it had to be completely redesigned for a new mission. It's a larger booster, and the mission profile is sufficiently different to where pretty much everything on the inside of the booster is different. There's well over 1,000 individual processes. Working with our customer, we were able to identify several hundred areas of improvement.
We've got totally new avionics on this vehicle versus what we had on shuttle. It's state of the art.
Bigger and more powerful than any previous launch system, the SLS has been under development for some time. Designing it is one thing, building it another. In new or refurbished factories and assembly shops, the body of the largest rocket ever to fly is being constructed one piece at a time. The massive hydrogen tank takes shape. The smaller oxygen tank soon follows. The interim stage for the manned flight is another hydrogen-oxygen motor supplied by cryotanks fabricated with new technology.
So to design and manufacture this tank, we use new materials. We process the tank by automated fiber placement. The benefit of that is we can lay down the material quickly, which provides us a low-cost operation and a very lightweight tank.
We've worked on this program for 29 months, and when we started, we'd never built a tank of this size by the methods that we did. We did automated fiber placement and fluted core, just developing the robotic fiber placement equipment and way to make the skirt in one piece was a large challenge.
Each exacting piece is fabricated, test articles are run through the mill, vibration tests, vacuum tests, acoustic tests, stress tests. Nothing is left to chance. technology and new materials for a new generation of space exploration.
For this test, there were several things that we looked at. This was the first time we used those thermal knives to start the deployment sequence, and that allowed cut some tethers, but then allowed the solar array to deploy. We wanted to test the locking mechanisms to ensure that it locked properly in space, because anything that could possibly go wrong, we wanted to test down here so that we can ensure our most successful flight.
It's all about technology. If you don't develop technologies for the future, you won't go where you want to go. So composites will decrease the weight of the tanks. It'll increase the payload performance of the launch vehicle. It'll give us, it basically enables things that we don't have today.
Soon the mighty rocket will lift human beings up further than ever before. The flight to Mars will be a long one, too long for a crew to sit in a capsule. Habitat and supplies will also be lifted to orbit and assembled. Several companies have been selected by NASA to carry out studies for a suitable system to do the job. A bit of competition is always good for invention. Bigelow Aerospace, with its expandable activity module, or BEAM, currently being tested on the ISS, will develop and test a prototype of X-Base, a 330 cubic meter expandable habitat. Boeing of Houston is developing a modular habitat system that leverages more than 15 years' experience in designing, developing, assembling on orbit, and safely operating the International Space Station. Lockheed Martin will refurbish a multi-purpose logistics module into a full-scale habitat prototype that will include integrated avionics and ECLSS. Orbital ATK will mature the mission architecture and design of their initial cislunar habitat concept based on the Cygnus spacecraft that now supplies the ISS. Sierra Nevada Corporation's space systems will study and refine a flexible architecture and concept of operations for a deep space habitat that draws on the lessons of 3 to 4 commercial launches to construct a modular, long-duration habitat. NanoRacks, in conjunction with its partners, Space Systems Laurel and the United Launch Alliance, referred to collectively as the Ixion team, will conduct a comprehensive feasibility study regarding the conversion of an existing launch vehicle's upper stage, or propellant segment, into a pressurized habitable volume in space.
So if you're designing spacecraft to be in the Mars orbit, then the studies we're doing on Space Station can be applied and help us design more durable spacecraft for that Martian atmosphere. MISSE stands for the Materials International Space Station Experiment. We do study the durability of polymers in terms of their mechanical properties with radiation exposure. And we hear a lot about the radiation exposure impact on humans for flights to, say, Mars. But polymers and other materials that are used on spacecraft can also degrade from radiation, and that's one of the things I study. The MISSE 8 experiments do take a little bit of time because we do very careful dehydration measurements of the samples after they've been in space. What we found is that the Teflon erosion rate is highly dependent on the amount of sunlight and possibly the heating too. you need to know which of these environments it's going to be exposed to because it'll erode at a different rate depending on the environment.
Assembling spacecraft in orbit and fueling them for the long journey to Mars sounds simple enough. On-orbit refueling is anything but simple. NASA have been developing a system for unmanned refueling for quite some time and have a test article on board the ISS.
We can take a pick-and-place robot, put the tool wherever we need it to be, and all it needs to do is drive that tool because the smarts are in the tool. So that's what we learned from working on Hubble, is you put a smart tool with the astronauts and accomplish, both things. You've got smart tools and astronauts working together. Now we're putting smart tools with robots and trying to accomplish the same type of things we did on Hubble.
Aimed at developing capabilities for servicing, even refueling spacecraft on orbit, RRM is like doing precise surgery at a distance, doctor and patient separated by the void and vacuum of space. It's tough, but the payoff is huge.
Robotics can do things that humans can't do in terms of precision, in terms of control, holding a particular spot for 6 hours while engineers on the ground debate what to do. We can't ask a human to do that.
The robot is a very stiff, rigid interface. It's not forgiving like an astronaut's hand, so we have to take that into account. When you push on something really hard with the robot, you build up really large contact forces. When the astronaut pushes on something, his wrist might give. He's got his own internal sort of software compliance running. But in order to accommodate the robot so we don't break anything, we have to build features into the tool, features into the software. Just getting the robot to go where you want it to go, and they don't position precisely. So you have to do things like build lead-in into the tool. An astronaut could probably just get it right on there because he's right there. So we do have to do things to make them, very specific to robotic operation.
That task successful? Next stop, Mars. The first manned mission to Mars will probably only orbit the planet, checking out all the gear and processes, even launching communication satellites and finalizing landing sites in preparation for the next mission, which will then make the descent to the surface. And that has a whole new set of problems to overcome. Unlike the Moon, Mars has stronger gravity, about 0.6 of Earth's, but it does have an atmosphere where parachutes can be used, although the atmosphere is very thin and not very deep.
Well, it's a funny thing about Mars, but if you take the average of the planet, the average height of everything in the planet, it turns out that most of the north is 2 kilometers below that, and most of the south is 2 kilometers above that. And it's just, we always land in the north because there's a lot more atmosphere. If we land in the south, it's like 4 kilometers less of air to come to a stop. In fact, at the altitude of the mountains in the south, the Mars Science Laboratory was still supersonic as it was descending into the crater that it was reaching in the north.
Assuming the need to pre-position habitats, supplies and equipment on the surface prior to a human landing, NASA and its partners are looking at several solutions. One is the HIAD, or Hypersonic Inflatable Aerodynamic Decelerator. This is basically a very large inflatable heat shield, much larger in area than the payload, able to slow the craft considerably faster than a standard spacecraft heat shield. Plans are to test the system on a payload from the ISS, utilizing a Cygnus resupply spacecraft. parachutes will further slow the payload to an altitude low enough for rocket engines to take over. Morpheus and the zombie flight systems have matured over the last few years and are capable of delivering cargo to a planet's surface autonomously, avoiding rough terrain or other obstacles without human intervention. Adding yet another building block to our human effort to explore the solar system.